All right, let's dive right into this explainer and crack a pretty high-stakes forensic mystery straight from the world of materials science. We're going to explore a technique that literally lets us look past the surface and peer directly into the atomic scaffolding of the universe.
Imagine you're working in a lab, and someone drops 4 separate vials of white powder right in front of you. To the naked eye, they are completely identical. There is absolutely no visual difference between them, their textures are the exact same, and they have no distinct smell at all.
Now, these could just be identical twins of the exact same harmless compound, right? Or one might be a perfectly safe food additive while another is highly reactive calcium oxide. Mixing them up? Yeah, that would be an absolute disaster. Standard chemical tests could destroy the sample or take days, but we need answers right now. We need something way faster and way more precise. Enter our secret weapon, X-Ray Diffraction, or XRD for short. It's basically the fastest, easiest, and most robust way to identify crystalline materials, what we call distinct phases of a solid. And the absolute best part? It's completely non-destructive. No melting, no burning, no dissolving our mystery powders to figure out what they are. You can think of it like this. Just like every single one of us has unique DNA, every crystalline substance out there produces a totally distinct XRD pattern. It's so specific that it isolates that one single material from literally every other mineral or synthesized substance on Earth. It gives us an absolute, undeniable fingerprint of the solid state. To really get how we capture this fingerprint, we've got to shrink down to the atomic level. Picture these repeating horizontal layers of atoms like perfectly stacked floors in a microscopic skyscraper. In XRD, we fire a monochromatic, so a single-color X-ray beam right at the material. As those waves hit these atomic floors, which are separated by a precise distance we call d, they bounce or diffract off the atoms. But here's the catch. For our machine to actually read a signal, we need something called constructive interference. It's exactly like pushing a kid on a swing at the precise right moment to make them go higher. The X-ray waves bouncing off the top layer of atoms and the ones bouncing off the bottom layer, they have to align perfectly in sync as they leave the material. The extra distance the lower wave travels has to equal an exact whole number of wavelengths. If it doesn't, the waves just cancel each other out and we get zero signal. And that magical moment of perfect alignment is captured by Bragg's law. Now, don't worry, we aren't going to get bogged down in the algebra here. Just look at what the math actually does for us. By simply knowing the X-ray's wavelength, that's the lambda, and measuring the exact angle it bounces off, the theta, this really elegant little equation lets us calculate those hidden microscopic distances between the atoms.
Thankfully, we are definitely not doing that math by hand. This beautifully complex piece of engineering, which honestly looks a bit like a prop from a sci-fi movie, is the inside of an actual XRD diffractometer. This is the hardware that actually goes in and measures those incredibly tiny atomic distances we were just talking about.
Now, despite looking pretty intimidating, every XRD machine really just boils down to 3 core components. First up, you've got an X-ray tube to generate our source wave. Second is a highly precise rotating stage called a goniometer. And this is exactly where we'll place our mystery powders to change that crucial theta angle. And third, a super-sensitive data collector, or detector, to catch the diffracted waves. Because Bragg's law demands absolute precision, our X-ray beam absolutely has to be a single, pure wavelength. The problem is, X-ray tubes naturally spit out a pretty messy mix of radiation, lots of stray waves bouncing around. So we use some really clever chemical filters, like nickel or zirconium, to absorb the unwanted rays. This guarantees that only a pure, pristine, single wavelength beam actually hits our sample.
Okay, but before we can just load vial number 1 of our mystery powders into the goniometer, we've got to do a little prep work. We have to grind our sample down to a very fine powder, specifically between 0.1 and 40 micrometers. Why so specific? Well, if the particles are too small, the signal blurs out. But if they're too large, the X-rays just scatter randomly and we lose the diffraction entirely. It's a real Goldilocks situation.
Once that prepped powder is scanned, the machine finally spits out our fingerprint, the diffractogram. What you're seeing is the intensity of the diffracted X-rays on the vertical axis plotted against their precise angular positions, those 2 theta values, on the horizontal axis. Every single one of those sharp spikes, that's a moment where Bragg's law was perfectly satisfied and constructive interference happened.
This one single graph basically holds all the secrets to our powders. The exact positions of those peaks along the horizontal axis give us the D spacing, which tells us the overall size of the atomic rooms inside the crystal. Meanwhile, the height or intensity of each peak tells us exactly how the individual atoms are arranged inside those rooms. It's pretty amazing when you think about it.
So, how do we actually use this to identify our identical white powders? It's pure detective work, and it follows a simple logical sequence. First, we get our pattern. Next, we find the exact angles where our peaks show up. Then, we look at the heights of the largest peaks. And finally, we take that unique signature and run it against the ICDD database, which is this massive library packed with reference patterns for over 100,000 known phases.
Take a look at this official reference card from the database. It's for sodium chloride, just ordinary table salt. By lining up just 3 or 4 of the strongest peaks from our unknown sample against reference cards exactly like this one, we can unambiguously crack the case of our mystery powders. And we do it without destroying a single grain.
But XRD isn't just for neat laboratory forensic tricks. It is deeply tied to real-world product performance. For instance, it tracks things called polymorphs. A polymorph happens when the exact same chemical decides to pack its atoms into a totally different crystal shape. Sometimes this happens just because the material was milled or stored a little differently.
And the stakes here? They're incredibly high, and they actually affect your daily life. Major industries rely on this to secure unique patents. Pharmaceutical companies use it to characterize complex drug formulations. A tiny 1% change in a drug's crystal structure can completely alter how it absorbs into your bloodstream. That subtle shift could turn a life-saving medicine into something totally ineffective or worse, dangerous. XRD is literally the irreplaceable quality assurance tool preventing that from happening. From decoding seemingly identical white powders in a lab to engineering the safe, high-performance materials we rely on every single day, X-ray diffraction gives us the ultimate key to the microscopic world. Now that we have the power to map the DNA of our physical reality, what hidden, world-changing atomic structures do you think we'll discover next?